Then the next one is recurrence relation. We'll divide that, and it's also not difficult to divide. So again, all these things that are not difficult to divide, you can. It also means that there's a possibility that it will be asked in COM. It has been asked in previous COM in quite a few times. So that's why I go through this derivation with you. So, I mean, you basically have very difficult to remember. Just memorize just by memorization is difficult. But just go through that and get the feelings that have the confidence you can redefine that without math handbook, because in the COM you don't have access to math handbook, unfortunately. So you need to just based on the question and just redivide that using what we are going through here. It's pretty straightforward, and we'll divide the recurrence relation between Bessel function of different order, and we'll use the generating function, which basically means that this recurrence formula we derive has the restriction using this derivation that they're integer order, but finally the recurrence relation actually apply to real order also. Right? So, but I mean, you can also divide the recurrence formula using the series solution. That is also possible, but that might be slightly more difficult than using the generating function. So we'll use the generating function. Okay, so we'll start with generating function. Again, write the relationship, the definition of the generating function. This is g x t is exponential function x over q t minus 1 over t, and that is equals to sum over n is n x e to the power n. Okay, so this is the generating function, and we can divide the recurrence formula. There are two of them, and the most straightforward way to divide it is take the derivative of g with respect to x and t. Okay, then we can see which one. I forgot which one, which derivative will give you which equation. Well, we can just try and see what we get. So there are only two of them, so why don't we try to take the x derivative first? Well, we will try to take the derivative. We try to take the x derivative that would relate to the derivative of j. That would be, I mean, listed in the text. The second one, we can try to take the t derivative first. That probably will give you the first recurrence formula, the first of them. So we take a partial g, partial t, and you can do a derivative on the left-hand side and then the right-hand side. Okay, and so the left-hand side is take the derivative of this exponential function, we give it the exponential, and then the same exponential function, take the derivative of the argument. And derivative of argument is x over 2, 1 plus 1 over t squared. Right. And then multiply by the same exponential function. And multiply by the same exponential function means the same g. right? But the same G is equals to that, so we can just write out. The reason is that we want to have a summation on both sides, and then we can compare power by power with the coefficient of each power, right? And then that is the same. And x, and this is just this one. Right? So that's the derivative on the of the left-hand side, and then the right-hand side is a little bit more straightforward. The derivative is just n d minus 1. N d n minus 1. Okay, and what you can do is I mean to compare the coefficient of the same power, you want to shift the coefficient so that they of the same dependent of t. So this is there's a t here. There's no t in here, and there's a t, and you want to change this to the same power. So let's just write it explicitly. So so for the first one is fine, right? For the first term is this, well, whatever it is, you can write it like the same summation, right? And let's keep it. Let's see if that would work. Because I mean, we can do it first, and then if that is not corresponding to the same form, we can shift it again, right? So this is this x. There's two terms. X over 2 times j sub n. That would be t sub n, right? And now the second term, you want to shift this because this becomes t to the n minus 2, right? To shift it, you need to some figure out. So t, this power is t to the n minus 2. If we want to get it the same power as the first term, which is just t to the n, right? That means this equals to t to the n prime. So basically, n equals to n prime plus 2, or n prime equal to n minus 2, right? So whatever you see n becomes n prime plus 2, and so that is second one. The n prime plus 2 is, now you can now change back to n, so n plus 2. Okay. Then t to the n. Yeah, everything is t to the n now. And likewise, you can do that. No, this one is n minus 1, so that's the same thing. This n minus 1 become n prime. This n plus 1, n, wherever you see n becomes n prime plus 1, so n plus 1, j n plus 1 is n. Yeah. Okay, so now compare. Now you can compare power, the coefficient of the same power. So this one of the t sub n coefficient and t sub n coefficient, they must be the same because the power expansion is orthogonal. I mean, they are linearly independent. So this each coefficient, so the coefficient must be the same. So you can combine that to say j sub n plus j sub n plus 2 equals to divide x over 2 to the other side becomes 2 to the x n plus 1 to n plus 1. Okay, and now this again, like what I said before, this is not the same form because the same form has this j sub n on the right hand side. So you can again shift it back. So if this is if the right hand side is n, j n, so n plus 1 becomes n, so n plus 1 becomes n, so this becomes j n minus 1. N plus 1 is n, this becomes j n plus 1. Okay, that's fine. So this is the form in your textbook. This is the first one. This is 14.7. Is that okay? So just in a few steps, we got the first one. Is that okay? So this process. So sometimes you just need a little bit try and error, but finally, if you do everything correctly, you'll get the correct result. All right. So that's the first one. All right. The next one. Now we can do the same thing now. Take the x derivative instead of t derivative. The partial g partial x goes to again take the derivative of the exponential function, give you the derivative of the argument, which is now simple. It's 1/2 t minus 1 over t. And they multiply by the same exponential function, which is the same summation. And by the way, I forgot to argue that we don't need to shift the index because both it covers the whole range. So and for this situation, it's easy. You don't need to shift the limit because limit is always minus infinity to infinity. So that's fine. That's kind of easy. Right. So that's the derivative of the left-hand side, and then the right-hand side is also straightforward. It's just enough space. So it becomes Jn pi because Jn depends on x. N pi means dj sub n dx, right? And then okay, so that is straightforward. And now all we need to do is do the same trick as we did each term. So this becomes the first one is t to the n plus 1. To the n plus 1, you want to change it to tn, so this becomes minus 1. So all the n in here become n minus 1. So you have 1/2 factor, jn minus 1 for the first factor. Right. And the second factor, this is n minus 1. This becomes n, so it becomes n plus 1. Right. So minus jn plus 1. And then t to the power n. And equals to the right-hand side. And so that one is, that's also 1/2 factor here. Okay. So that is actually easy. So this one compared with this one, this equals to this one. So means jn minus 1 minus jn plus 1 equals to 2 jn pi. Oh, yeah, so that's the second one. It's okay. So straightforward, right? So you know, so if you are asked to we divide it, it's straightforward, right? So hopefully, I mean, it's just a few steps you can get this recurrence formula, and there are a few consequences of this immediate consequence of this recurrence formula. So 14.9 to 14.12. 14.9 is some special cases. So basically setting n to 0. For this one, if you set n equals 0, so right-hand side is 0, meaning j minus 1 plus j plus 1 is 0, which means that they are negative of each other, which is we have already seen before, because remember for integer order, j minus n is minus 1 jn. No, so j minus 1 is minus j1. So this is for n equals 0, so you can get that. For n equals 0 in here, that is different because this is a minus sign. So this is j minus 1 minus j1, and then using the same relationship, this becomes a minus 2j sub 1 equals to 2j sub 0 pi. So that give you the derivative. J0 pi is actually minus j sub 1. So that a neat special relation. So the derivative of the zero order Bessel function is given by the negative of j sub 1. So that sometimes is useful. Okay, and the rest are 14.10 to 14.12 are not difficult to derive. So those exercise will be the exercise in the homework question. So that's fine. Okay, up to here. So we'll not go through that those relations. It's just mathematical property you can derive from these two. So these two are fundamental, but you can, for convenience, you can derive other additional relationships that in some situation just help you, like the intermediate step to derive other things. Okay, so that's all the recurrence formula for integer order, but then we can generalize that, just change n to nu, and then they will satisfy the same recurrence formula. Okay, is that okay?